Hi, I'm Guillermo. Today I'll be presenting Improved Price Oracles, Constant Function Market Makers, a paper that I co-authored with Tarun in kind of the wake of this decentralized finance craziness that has become a mainstay, it seems, of the Ethereum community and those interested in the intersection of traditional finance and blockchain technology. So we'll quickly review some history of the classical automated market makers and how they apply, and kind of note that there's a separation between the beast that is the classical automated market makers and the constant function market makers that we present here. But in some sense, they're kind of kindred spirits, even if they need not be directly comparable. So very generally speaking, right, in a financial platform, we need some way of trading assets and then measuring assets' relative prices. This is normally pretty easy, right? Essentially, you go up to someone on the street and you say, look, I'm selling this thing. Are you going to take this? Or look, I'm buying this thing. Are you going to take this amount for this thing? In the general traditional setting, kind of in the case where there's a lot of buyers and sellers, this leads to order books. Here, buyers post bids of the maximum price they're willing to buy for, and sellers, of course, post asks, which is the minimum price they're willing to sell for. And whenever there's a crossover, in other words, whenever a buyer is willing to pay more than the minimum ask price, then the trade is executed. We've kind of, mentioned this very offhand, and we kind of say that things very casually, but it turns out that things like, for example, a trusted party keeps a record of outstanding bids and asks. That has a linear space requirement, which, while it's not particularly difficult to handle in day-to-day life in a centralized manner, in a decentralized manner, this becomes very quickly expensive whenever there's a lot of participants. Another thing we mentioned kind of offhand is, say, look, when the highest bidder bids more than the lowest asker, right? But this implies that the price may update slowly, right? Especially whenever there are a small number of agents actually performing bids and asks. Another thing that kind of happens in the centralized exchange world, which is potentially very difficult in a decentralized one, is that exchanges usually end up adding subsidies to ensure there's enough liquidity to actually perform a good number of the trades or to bootstrap their exchange. So one idea is the notion of automated market makers and logarithmic market scoring rule, as initially studied by Savage back in 1971 and then popularized by Hansen in 2002, is to use a simple formula to determine the asset price. In this case, liquidity providers pool their assets, let's call them A and B, into what we're just going to call reserves. These are just general boxes that have X amount of asset A and X amount of asset B. In this case, of course, as one might expect, if the liquidity providers or the formula sets the price too low, then agents, of course, will purchase the reserves at the current price. And if the price is set too high, then one might expect that agents are going to be incentivized to sell to the reserves at the current price. Using this notion, one idea is to simply set the price based on how much asset is remaining in reserves. For example, if too much of asset A remains when compared to asset B, then one thing to simply do would be to just decrease the price of asset A, therefore incentivizing people to buy asset A when relative to asset B. The simplest example of such an automated market maker is to say, look, the price that I am selling asset A relative to B is fixed, right? This is at any reserve, I will simply sell you asset A for X amount of asset B. Another slightly more complicated example, and surprisingly popular, is just kind of the next natural extension. You say, look, actually, what if we make the reported price just the ratio of the reserves of each of the assets? And in fact, this curve, as given, is exactly Uniswap. It's probably the most popular constant function market maker or automated market maker available in practice. So kind of a brief global size overview of AMMs is, again, as we mentioned, Savage in 71 and Hansen in 2002 have logarithmic market scoring rules, which, as we know, can be used for AMMs and are very obviously used in prediction markets. Then Chen and Pennock realized that there's very general formulations that exist that kind of underpin AMMs and then construct more markets based on these axiomatic formulations. Othman and Sandholm in 2010 then derive this notion of liquidity-sensitive AMMs that in general do not have unbounded loss, or have, in other words, very explicitly bounded loss. Then Othman and Sandholm in 2011 derive constant utility automated market makers for prediction markets, which are kind of starting to get close to a similar thing to constant function market makers, at least at a surface level. And then Buterin, Koppelman, and Liu in 2016 realized that you can kind of extend the broad idea of AMMs to this notion of constant product markets, or Uniswap, and realize that this actually gives an immediate application in exchanges and as price oracles. So what is the current state of automated market makers in 2020? Uniswap and many other constant function market makers have actually reached an astounding $23 billion of trading volume. Part of this growth appears driven essentially by the ease of use of decentralized exchanges, which automate a lot of the decisions that users have to do. In some sense, kind of like an index fund for decentralized exchanges, except not quite as sophisticated. So we're going to first discuss some quick definitions and properties of constant function market makers before kind of getting into really the meat of the paper, which are these notions of the reachable set and path efficiency. Very broadly, any CFMM, constant function market maker, is defined by a trading function. The function's only purpose is simply to map the reserves, the input amounts, in other words, how much money the trader has put into the contract, and the output amounts, in other words, how much money the contract is willing to give to the trader, to a real number. Note that all of these are quantities in Rn, of course, because we could potentially be trading N coins for N other coins. In this case, the contract accepts the trade if and only if the function, when evaluated at the trade amounts, is equal to the function when evaluated at 0, 0. In other words, trades are essentially accepted if and only if the function value is kept constant. And then, as one would expect, of course, reserves are simply updated by adding in what the trader has put into the contract and removing what the contract has paid out to the trader. In all of these examples, we're going to have a fee, but here are some very basic constant function market makers and their trading formula. So Uniswap is essentially a constant product market maker, whereas we note the product of the new reserves minus some percentage fee needs to be constant. A similar thing with Balancer, which is also sometimes called the constant mean market maker, essentially says that the geometric mean, again, with the fee taken out, needs to remain constant. And then just to kind of show how crazy such constant function market makers can get, we have Curve, which is essentially an affine function minus the reciprocal product of the reserves, needs to stay constant. Surprisingly, Curve is actually an extraordinarily popular exchange, even though it seems particularly complex for things like stablecoin pairs. We've seen a lot of functions, right? They're potentially kind of very crazy, and so it's not clear how to give simple definitions for the things that we care about. So in order to do that, we're going to introduce the reachable set. In particular, if we notice, right, in the constant product case, or in the constant mean case, there really are only a small number of reserves that are ever reachable. In other words, when we make a trade, there are only a small number of total reserves that we can reach. We can't reach all of the n vectors that have positive entries, right? We can only reach a very specific subset of such reserves. So in order to kind of fix this idea, we're going to introduce a reachable reserve set. This is going to feel a little ad hoc, but it's actually quite natural. The idea is we're going to simply say that the reachable reserve set is a set of all values, or all reserve values, that can be reached within a single trade, and also those trades which are strictly worse for the trader. In other words, the trader put in potentially too much money or got out less money than they should have. This notion is very, very similar to the epigraph and optimization, and we'll make it quite concrete in a second. Let's just take the very basic example of Uniswap. If we plot the reserves that can actually be reached for Uniswap, essentially all we get is a hyperbola. As previously stated, Uniswap is the constant product market maker. In other words, the market maker such that the product of the reserves is kept constant. In this case, the constant is 1. So R1 times R2 must be equal to 1, which draws exactly a hyperbola. As before, traders can exchange coin in this general CFMM with the only condition that the reserves after the trade must remain on the hyperbola. Then the reachable set, as we have defined previously, essentially the set of all points above and to the right of the hyperbola. Since, of course, we've only added points, all of the reserves that were previously reachable are certainly still reachable. But there's one important thing to notice, and that's essentially that no rational trader is ever going to pick a point inside of the set itself. And we're going to call the set of points which are inside of the set the dominated interior, because there exists at least one trade that is strictly better for the trader. So one thing to notice that we can kind of generalize to a lot of CFMMs is that the resulting set, for example, is convex. As we mentioned before, it's approximately easy to optimize over. It's not hard to show that essentially all of the big CFMMs that are known are convex. Another thing that's important is that it's essentially unique over all trading functions, at least for rational agents. There are many trading functions which lead to a specific reachable set, but this might not be true the other way around. And I think that's, of course, very important practice, that it's actually easy to write for most CFMMs that we care about. And a particular thing that's very useful in theory is that it leads to simple definition and proofs of things that we care about for a CFMM. So we'll discuss the notion of path deficiency. So we say that a CFMM is path deficient if the reserves that can be reached from the current set have a reachable set that is no larger than the current reachable set. In other words, as traders trade with a contract, the possible future set of reserves never gets larger. There's never more points in one than the other. In this case, all currently known CFMMs are in practice path deficient. One simple implication of this, that's kind of a one-line proof, is essentially that, look, if you give me any price C, the profits of liquidity providers will never decrease below some fixed threshold. And the proof essentially follows immediately from the fact that the set of reachable reserves at time 0 must be at least as large as the set of reachable reserves at time t-1 by definition of path deficiency. Note that all of these properties are actually quite different from LMSR and classic AMMs. There's not really a notion of path independence in this case that's actually actively important, other than in very specific scenarios. Another idea is that a very similar proof actually shows that traders, which include arbitrageurs, are not incentivized to split up their trade into a bunch of smaller trades. This implies that essentially the arbitrage problem that says, what is the best trade I can make right now, versus the arbitrage problem that says, what is the best sequence of trades I can make at any point in time, have equal optimal values. So arbitrageurs are never incentivized to break up their trade, and in many cases are incentivized to solve their problem as quickly as possible. In this case, the optimality conditions of this one-step arbitrage problem imply that the cost vector C is actually a supporting hyperplane of the reachable set at the optimal point. So, in other words, what we're saying is simply, if you want a CFMM to report a price that is equal to the actual market price under no arbitrage conditions, then the CFMM should report essentially the supporting hyperplane at its current reserve value, up to some scaling by a numeraire. So in this case, while 1/2, 2 is a supporting hyperplane at reserves 1, 2, then you would say that the price of coin 2, in this case, is 4 relative to the price of coin 1. Simply because we've scaled both entries by 2, such that we make coin 1 the numeraire. Additionally, it is not hard to show that no arbitrage will also imply that the exact total reserve value at a specific price is given by the infimum over the reachable reserves of C transpose R prime. An interesting and immediate implication of this is that the CFMM, if it can be written in the following way, essentially has this what appears to be more complicated expression for its total price, but is actually much simpler than the original, because this is now an optimization problem over one variable as opposed to an optimization problem over n variables. And additionally, it's not hard to show that this problem is always convex. One thing to note is that this definition immediately implies that the price is concave in C. That's simply because minimizing over a family of functions that are linear in C always results in a concave function. In general, the second problem that appeared more complicated can actually be used to give closed form solutions for the reserve value. So for example, in Uniswap and Balancer, it's not hard to show that the total reserve value is proportional essentially to the geometric mean of the cost vector with the same weights. But of course, very generally, it need not be the case that it has a closed form solution, as we found out, for example, when attempting to do so with curve, which is a much more complicated formula. In conclusion, we kind of have a few things that are of interest. So the big picture idea of all of this is the study of CFMMs is interesting not when you study their functions directly, but when you study these resulting sets. So in some sense, you've removed all of these possible equivalences between functions by just considering this reachable set. This notion of a reachable set then gives like very clean definitions, as we've shown before, for kind of things that we care about, things like total reserve value or the reported prices. Another important thing is that because these sets are usually convex, it implies that arbitrageurs can easily solve most problems, computationally speaking. So therefore, what we expect is that the CFMM will report correct prices under this model. And perhaps most importantly, as we would want of any good theory, is that all of the known current constant function market makers in practice satisfy the conditions that we've provided here. And of course, we encourage you to read the paper for far more results and interesting things that kind of appear when you try considering cases with fees. We would like to quickly acknowledge some people which have been invaluable in writing this paper, and that's Tim Refgarden from Columbia, John Marr from Gauntlet for editing the paper itself, Shane Barrett from Stanford for taking a look at the slides or some very early version of the slides, and then Alex Evans from Placeholder, who pointed out in one of the early drafts of the paper that we could actually generalize some of the analysis slightly. Thank you.